What is hyperbolic geometry? Hyperbolic geometry is a non-Euclidean geometry discovered by assuming only the first four of Euclid's postulates and replacing the parallel postulate by its negation, which is called the hyperbolic axiom. We will explore the hyperbolic axiom in more detail after we've talked about exactly what hyperbolic geometry is and lines in hyperbolic space. In order to visualize hyperbolic space, we must first talk about what curvature is. If you think about the Euclidean space, planes are flat, so planes in Euclidean space have zero curvature. Spherical space is different than Euclidean because its surface has a positive curvature. And hyperbolic space has negative curvature, and we'll discuss positive and negative curvature on the next slide. If you're talking about positive curvature, then no matter where you are on the sphere, it curves the same way in every direction. Hyperbolic geometry is an example of negative curvature. And negative curvature means that movement in negative space is different depending on your direction. So let's take a look at the saddle, which is an example of negative curvature. If you start at the front of the saddle and move toward the back, you first have to move downward and then upward. However, if you start at the right and move to the left or left to the right, you have to travel upward and then downward, so the direction is different. Examples of negative curvature in nature include lettuce and a coral reef. Before we move on and talk about models of hyperbolic geometry, here's a quick note. The models of hyperbolic geometry do not look like the hyperbolic plane. They serve only as a means of exploring the properties of the geometry. So all of the properties of hyperbolic geometry are true in each model. They are just various ways of looking at and thinking about hyperbolic geometry. So let's take a look at the Weierstrass model. This is an infinite model where the entire hyperbolic space is represented on the surface of a hyperboloid. This model will lead us to a second model that we will use to explore hyperbolic geometry for the remainder of the lesson. The Poincare disk model is obtained by a projection of the Weierstrass model. It is an inversion of the upper half plane and will transform the upper half into a circular disk without boundary. So if you imagine standing at the point marked Poincare and looking up at the disk, what you would see is a circle from your point of view, but the circle would have no boundary because this is a paraboloid without end. Now let's explore lines in hyperbolic geometry. The definition of a line using the Poincare model is an arc of a circle that is orthogonal with the circumference of the disk. So basically what that means is that each line on the Poincare model forms a right angle at the circumference. Let's take a look at lines on the Poincare disk using the software non-Euclid. Let's start by plotting 2 points to draw our line, and draw the line through these 2 points A and B. And let's move the points, and notice no matter where we move points A and B, the line is always perpendicular to the circumference of the Poincare disk. Also notice that this line will become straight in a Euclidean sense when this line passes through the center of the Poincare disk. Let's explore Euclid's first postulate about lines and see if it holds in hyperbolic geometry. So let's start by plotting some points and constructing a line. And we indeed have constructed a line. And let's maybe plot some more points and construct a line. Let's see if we can construct AC, and we can, and it is a unique line. Line AD is another unique line, and line AE is a unique line. So no matter what 2 points we plot on this Poincare disk, we can always construct a unique line. Let's take a look at Euclid's second postulate. Any straight line segment can be extended indefinitely in a straight line. Let's see if this holds true in hyperbolic geometry on the Poincare disk. If you look at line segment PQ, we could extend line PQ through point R, and beyond point R it would still continue infinitely because the edges of the Poincare disk never end. Likewise, if you extend it to the left, it would still move on indefinitely. So Euclid's second postulate holds in hyperbolic geometry, and the same can be said for any line on the Poincare disk. In how many points can two lines intersect on the Poincare disk? Well, in Euclidean geometry, two lines can be parallel, which means there is no intersection. They can intersect at a single point, or if the two lines are the exact same line, then they will intersect at infinitely many points. Let's see if the first two of these hold true in hyperbolic geometry. Let's explore two lines on the hyperbolic plane to see what happens. So let's draw line AB and line CD, and let's move them around. It's possible for lines AB and CD to never intersect. So therefore they would be parallel to each other and have no point of intersection. It is also possible for us to move this line CD in such a way that it will intersect line AB at a single point. So in conclusion, 2 points on the Poincare disk can intersect not at all or just once. In Euclidean geometry, given a line and a point not on the line, there exists a unique line that passes through the point parallel to the given line. Let's explore this postulate using the non-Euclid software. The parallel postulate is what makes hyperbolic geometry unique from Euclidean geometry. So let's explore that. Let's draw a line AB and a point not on this line, point C. Let's see if we can draw a line through point C parallel to AB. So let's draw line CD. Notice lines AB and CD go off in different directions and they will never intersect. So they are parallel. Let's see if we can draw another line through point C parallel to line AB. Let's draw a line CE. This line will also never intersect. Line CF and line CG. All of these lines are parallel to AB and will never intersect AB. So we can draw infinitely many lines parallel to AB through point C. So to sum up the hyperbolic axiom, there exists a line and a point not on the line such that there are at least two lines passing through this point and parallel to the given line. Lines in Euclidean geometry are of infinite length. Can the same be said for lines in hyperbolic geometry? If you think of the Poincare disk model, since the edges of the circle go on infinitely, the lines also move on infinitely. So the same can be said of lines in hyperbolic geometry. Now let's explore triangles in hyperbolic geometry.
Hyperbolic triangles consist of three non-collinear points connected by three line segments, much like triangles in the Euclidean plane. However, the sum of the angles of a hyperbolic triangle is always less than 180 degrees. This difference in angle measures is due to the curvature of the varying plane. Using non-Euclid software, we can create various hyperbolic triangles in order to investigate the sum of the angles of a hyperbolic triangle. Start by drawing the three vertices of the triangle and connecting them with line segments. Then, by selecting the Measure Triangle tool, we can find the sum of the angles. After creating these angles on the Poincare disk, as the side lengths become longer, you will notice the angle measurements grow smaller. Look at the triangles and their measurements listed below. The edges of the Poincare disk used to model hyperbolic space extend to infinity. As the vertices of the triangle start to approach infinity, the angle measurements grow smaller. What would happen if the vertices of the triangle were positioned on the edge of the Poincare disk? When all three vertices of a hyperbolic triangle are positioned on the edge of the Poincare disk, they are called ideal triangles. The vertices of an ideal triangle extend to infinity. This constant extension also causes the sides of the ideal triangle to extend infinitely. Therefore, the sides of the triangle will never meet. The sides will only move closer together infinitely, creating an infinite perimeter. When creating an ideal triangle using the non-Euclid software, we can create vertices very close to the edges of the Poincare disk. Here, we can see the angle sum measure to be very close to 0 degrees. In fact, the sum of the measures of the angles of an ideal triangle will always equal 0 degrees. Spherical triangles lie on a finite plane with curvature. These triangles have an angle sum range of 180 to 540 degrees. Triangles that lie on the Euclidean plane have no curvature and have angle sums of exactly 180 degrees. Hyperbolic triangles, in comparison, lie on an infinite plane that also has curvature. Therefore, these triangles will always have angle sums of 0 degrees and can also be extended infinitely. How is hyperbolic space used in practical applications? Artist M.C. Escher is known for creating unusual and almost impossible-looking structures in his works of art. In Escher's Circle Limit series, he uses hyperbolic space to give his patterns a sense of infinite growth. Here are some examples of Escher's circle limit. When the patterns that Escher created move toward the edges of the circle's circumference, they seem to continue infinitely. These are not unlike the ideal triangles that are mentioned in the slides above.